Welcome back, everybody, to section 1.4, exponential functions. All right, many of you should be watching today. We have a couple people out today, so this should be a popular video. Section 1.4, exponential functions. Now, we've covered exponential functions all the way back probably to Algebra 1. You've studied exponential functions. But we're going to talk about them a little bit more theoretically and talk about them like a little bit more in depth in here. Okay. So our most basic exponential function is 2 to the x. 2 to the x, that's like our parent, right? 2 to the x. We don't make it 1 to the x because 1 to the x would just come out to 1 every time. 1 to the any power is 1. So our most basic parent function of an exponential is 2 to the x. Because the variable x is the exponent, that's what makes it an exponential. Once we put the variable in the exponent, that's what makes it an exponential function. It should not be confused with the power function x squared. X squared and 2 to the x are not the same thing, and we're going to compare them in a second. Okay? In which the variable is the base. The variable is now in the exponent. In general, an exponential function is a function of the form f of x equal to b to the x, where b can be any base. In general, there are a few exceptions to that, like if b is 1, like if b is 0. Like there's exceptions to that, where b is a positive constant. Notice that takes out a lot of possible bases, where b is a positive constant. So therefore, that means 0 is not positive. 0 is neither positive nor negative. So b has to be anything above 0. b cannot be negative. We're not going to talk about when our bases are negative. Same thing with, we're going to talk about logarithms here coming up tomorrow or the next lesson. Same thing there. The bases cannot be negative there as well. Let's recall what that means. So remember that any power, b to the n, is going to be the repeated multiplication n times over on itself. Okay? N factors of b. If x is 0, then b to the 0 is 1. So if x is negative and where n is positive, or n is a positive integer, it's just going to be a negative. It's going to flip, right? The base cannot be negative, but the exponent can be negative, right? We know what happens with a negative exponent. It just flips down into the denominator. If x is rational, x is equal to p over q, where p and q are integers. Basically what happens is the numerator of your fraction, the numerator of your fraction is the power, the denominator of your fraction is the index. So if I've got like x to the 1/2 power, actually I should say, like 2 to the 1/2 power, that means 2 to the first power and the square root of that, right? If I've got 3 to the 3/4 power, that means this is 3 to the 3rd power and the 4th root of that. That can also be interchanged. That's commutative. We can also take 3 to the, the 4th root of 3, then cube it, if we would like to. Okay? You can either do the numerator first or the denominator first. Okay? All right, so let me show you some graphs. The graphs of members of the families of functions y is equal to b to the x are shown here in various values of the base. Notice that all of these graphs pass through the same point, 0, 1. I got to scroll down a little bit. 0, 1. They all pass through 0, 1 because if you take any base, raise it to the 0 power, it's always 1. That can be a big number, small number, doesn't matter. Fraction, anything. And raise it to the 0 power, it is always 1. This is 1/2 to the x. This is 1/4 to the x. This is 10 to the x, 4 to the x, 2 to the x, and 1.5 to the x. Notice what's happening here. As soon as it shifts from a number less than 1 to a number greater than 1, it's going from a decay to a growth. So what happens at 1? Well, it flatlines. It's not an exponential anymore. 1 to the x is not exponential because 1 to any power is just 1, right? So if whatever I plug in, it's just going to be 1. The output is always going to be 1. So it actually turns out to be a horizontal line. So we can go from 1/2 to 1/4. See, it's getting a little bit steeper decay when I increase the size of my fraction. I should say decrease the size of my fraction. Increase the size of my denominator. It's going to get steeper and steeper as it decay until it hits 1, and then it flips up over into a growth. As soon as I change from a number less than 1 to a number greater than 1, it changes into a growth. And now, as soon as I make my base bigger and bigger and bigger, that growth keeps getting steeper and steeper and steeper, which is something we should expect, right? 2 to the x is not going to have the same same as fast growth. I'm saying that way wrong. Same as fast as growth as 10 to the x. Okay. You can see from figure 3 that there are basically 3 kinds of exponential functions. Ones that are between 0 and 1, one where base is 1, and I wouldn't even call that an exponential function. And if b is greater than 1. These 3 cases illustrated down below Observe that if b is not equal to 1, then the exponential function b to the x has domain, all real numbers, but range 0 to infinity. Take a look at that. What's wrong? Somebody saying
Mr. Butterfield came in here, stood here for like a solid minute.
He did? Are you serious?
Yeah.
Wow.
There are like 3 people in here.
I know. And you know what's funny? Only 3 people are gone.
Really?
Yeah, that's the funny part.
Nice.
It's
He just asked if this was Spanish.
yeah. They were like, Mr. Butterfield just came in here for a minute.
He was standing here for quite a while.
Yeah, I didn't even notice him. I was on a roll, man. I'm grooving. Yeah, I get locked in. I'm wearing it. You can't even. You can throw stuff at me. I wouldn't change. The domain is all real numbers. The range, it depends on whether it's. It doesn't depend. It doesn't even depend on whether it's a number less than 1 and a number greater than 1. The range is always going to be positive numbers. Take a look. Do I ever go below the x-axis? No, never. And actually, I do this thing where I get closer and closer and closer to the x-axis. Remember, that's called an asymptote. It's never going to touch. Never. Can't touch it. Notice that since 1 over b to the x, 1 over b to the x is 1 over b to the x is equal to b to the negative x. The graph of 1 over b to the x is just a reflection of the graph of y is equal to b to the x about the y-axis. Okay, so what am I looking at here? Basically, I'm saying that I can plug in any number. I can take x and make it anything that I want. I can take any base and raise it to any power that I want. But the range is never going to go below the x-axis. It's always going to turn out to be a positive number. You can't take a base, you can't take 2 and raise it to any power to make it negative. That's not gonna happen. You can't change the base and turn out to make it to be negative. One reason for the importance of the exponential function lies in the following properties. If x and y are rational numbers, and these laws are well known from elementary algebra, it can be proved that they remain true for any arbitrary real number x and y. So we've learned these way back in Algebra 1. These are just the exponent rules that we have. Remember that if you're multiplying with like bases, you add the exponents. Okay, you want to take a quiz? See, I noticed her. I saw her. Mr. Butterfield just came in and I didn't even notice. How did I not notice him? He's like the loudest person in the world.
He really like just
He didn't say anything. No. He didn't say anything. Okay. I'm sorry if there's ever an intruder. Like, I'm probably not going to notice. All right. Like bases, b, they've got to be like bases. B to the x times b to the y is b to the x plus y. And that's interchangeable too. I can go forward and backward here. B to the x minus y. Subtraction means division. Power to a power means we multiply. B to the x to the y is b to the xy, where I multiply x and y together. And then if I take a product, a times b to the x, I can basically distribute that product. Now, please don't confuse this. I am not saying that a plus b to the x is a to the x plus b to the x. That is not the same thing as a times b to the x is equal to a to the x, b to the x. Okay? Be very careful about this. This does not distribute like this does. Okay? You can distribute here because this is a product. You cannot distribute here because this is a sum. So you can distribute if it's a product but not a sum. All right. Sketch the graph of the function y is equal to 3 minus 2 to the x and determine its domain and range. All right, so if I want to graph this, maybe the best thing to do is to, well, I guess it's a scratch. We're not going to sketch, so we're not going to put it in our graphing calculators. But maybe the best thing to do would be to look at the transformations that have happened. Because we know the parent, we know this exponential parent of 2 to the x is in this kind of general. You coming to take your retake?
Yeah.
Hold
Lots of full focus.
I know, now you got me rattled. Nope, that's our guy. No. What says retake on here?
Thank you.
Okay, so there's our parent 2 to the x. Right, this is just 2 to the x. There's a couple ways we can think about it. I would tend to reorder this. I would say y is equal to negative 2 to the x plus 3. And then you have to think about, okay, what comes first? I see an up 3 and a reflection, right? I see an up 3 and a reflection. Well, what should come first? Do I reflect first and then go up 3? Do I go up 3 then reflect, or does it even matter? Well, here's what I say to you. If you were to plug in a number, what would happen first? Would the reflection happen first, or would the up 3 happen first? The reflection would happen first. So that's what we would do first. We would reflect. And is that reflect over the x-axis or over the y-axis? If we're gonna, if it's a negative down below, okay, that means it's a vertical reflection. So it's a reflection over the x-axis. Okay, reflect over x. If it were a reflection over the y-axis, it would be happening within the exponent. Because if that was a negative up in the exponent, that would turn it into a fraction, which would make it not growth, but decay. Okay? And then the second thing that would happen would be the up 3 units. Okay. Is that Buck again?
Yeah.
Yeah, I heard you because you were talking this time. Buck. Mr. Buckfield. Yeah, I heard you now because you were talking.
No, I was in there.
They were like, you guys sitting there for like a minute.
No, but I was watching, man.
I was locked in.
What is
I
he?
was zoned in.
What is he talking about? I asked Wolf, I said, is that Spanish? And I didn't understand what he said.
I was in the zone. I'm wired in.
They're thinking the same thing.
You could teach it too?
No.
Oh, no? Oh.
Definitely no amendments,
We have no
that's
idea
for
what
No
sure.
amendments, but that's, okay.
Yeah, I would flunk the amendments.
We took like
So it's like
Oh, really?
20 amendments.
I know the Fifth Amendment.
Literally every week.
Double jeopardy. Or you can't incriminate yourself.
Same thing.
Oh, that's
It's
it?
both, yeah.
Oh, really? That's Fifth too?
17th Amendment,
I don't know.
joint election of senators.
Yeah, see, I don't know those. Yeah. I know how to graph an exponential function. I can do that. All right. So that's what I'm going to do. I'm going to reflect it over the x-axis, then I'm going to go up 3 units. Okay, so reflection across the x-axis would just take this, leave. Oh, that's the y-axis. I'm smart. Thank you. So that's a reflection across the x-axis. And now I'm going to go up 3 units. So this went down to -1. This is going to go up to 1, or up to 0, then up to 1, now up to 2. So here. The green is what we want. That's the sketch. So if you're ever confused about what transformations happen first, thinking about if I plug in a number, what would happen first? Go with the order of operations. Okay. Interestingly enough, I could have factored out a -1. If I really wanted to, I could have factored out a -1 and said, okay, -2 to the x minus 3, because those things are equivalent. Now, in this case, what would have happened first if I plugged in the next value? What transformation would have happened first? A down 3, then a reflect. Would that look the same if I shift this down 3 units and then reflect it over? Yeah, that would have looked exactly the same. So no matter how I work the problem, if I work with it algebraically, and which would change the order of operations, it should still end up on the exact same spot. Okay. All right. Use a graphing device to compare the exponential function 2 to the x and the power function x squared. So we talked about how we should not confuse them with each other. So let's look at how they're different in terms of their the look of their graphs. And to do this, I'm actually going to jump to Desmos because I think it's a little bit easier to graph using Desmos when we look at exponentials. Desmos. So I'm going to look at 2 to the x and then 2 to the x and then look at x squared. Now, if I'm only looking at I think this is like a, what, 10 by 10 graph almost, right? I guess I got -6 to +6 and -10 to +10. When looking at this, it looks like, okay, here's my exponential coming across. Okay, here's my exponential. And then I see my quadratic, and it crosses right here at 2, 4. So it looks like at some point it's going to overtake it, and it's going to say, okay, at 2, 4, my quadratic is going to grow faster than my exponential. Is that going to be the case as x gets large? So I see one intersection point here at 2, 4. I do see another intersection point here. It actually crosses it twice right here, as I see on my graph. So let's see. Is it going to overtake it again? Yes. It is going to overtake it again. I see actually 1, 2, 3 intersection points. There are 3 intersection points with this, not just 2. So I see my quadratic now go underneath, go to the, now it looks like my quadratic is not increasing as fast as my exponential. So as I get larger and larger with my x values, and we're going to talk about what that means mathematically, we're going to say as the limit approaches infinity, what gets bigger faster? We're going to need to examine that a lot. What's going to grow at a faster rate? What's going to be the bigger rate of change? We're going to answer that question a lot. But looking at it, the quadratic as compared to the exponential, it actually crosses 3 times. It looks like for a while that the quadratic is going to be bigger than the exponential, but the exponential overtakes it at my x value of 4. By the 4th unit, the exponential takes back over, and it's growing faster and faster and faster than my quadratic. And then for any x value beyond that, my exponential is going to be bigger than my quadratic. Now, what are the applications? What are the applications? Well, there's tons of applications, a lot of real-world applications. Man, I mean, just look at the pandemic. We talked about how, for a long time, there was this thing called the R value that they were really concerned about. And they were saying, okay, we want to keep the R value less than 1. If the R value is less than 1, that's a good sign. If the R value is bigger than 1, that's a bad sign. What does that R value really mean? It means that, like, if, say the R value is 2, that means one person is going to infect 2 people. On average, one person is infecting 2 people. So that's going to grow at a really fast rate. You know, I've got my case 1, and then that person's going to infect 2 people, and then that person, and then that person, and that person, that person, that person, that, and so by day 3, it goes from 1 to 8, which would make sense. That's 2 to the 3rd power, right? However, if you can keep that number low, if you can keep that number less than 1, that base less than 1, it's not going to grow anymore, it's going to decay. So thinking back all the way to this, what we were trying to do with the R value was trying to keep it, either at 1 or below 1, because if we can at 1 or below 1, it's going to the values are going to decrease rather than increase. As soon as that R value flips to something bigger than 1, it's going to keep growing and growing and growing and not decreasing and decreasing and decreasing. Okay. Population has this tendency to exponentially grow or exponentially decay, especially like bacteria. Yeah, this is the example. Considering population growth of bacteria, that's going to exponentially grow or exponentially decay. There is radioactive decay as well. Population function. This population is a constant multiple of the exponential function 2 to the x, so it exhibits the rapid growth here. What about the human population? Table 1 shows data for the population from 1900 to 2010, it looks like. Okay, do we see a general exponential growth? I mean, it almost looks like it might level back off up in here, but we see a general exponential growth. We could put this in our calculators and find an exponential regression for this equation. And there it is. Okay, the book actually does it for you. And it shows that this is exponential. And it's actually a pretty good fit. The R value, and the different R value, the correlation coefficient is actually pretty good for this. It actually fits pretty well to it. Interestingly enough, when does it drop below my expectation line? Well, what's happening from 1930 to about 1960? Well, like wars and depressions and stuff, right? So it makes sense that the population actually dipped below it. It was tugging that line a little bit down. Okay. But what moral of the story is that we can model exponential growth using a wide variety of real life examples. Same thing with exponential decay. This is one example. In 1995, a paper appeared detailing the effects of this drug on the HIV virus. Table 2 shows the values of the plasma viral load, basically how much is in the body, the viral load of a particular patient using this drug. So basically it was saying that, okay, is this drug truly working? Yeah, it really is. Is it going to make it go down to zero? Probably not, but it's going to make it keep getting smaller and smaller and smaller and smaller. Okay. Same thing here. This is an exponential function. Oh, that's the same exponential function. Oh, but another thing that we can talk about is half-life. Half-life. Now, we covered that back in Algebra 2. We're going to logically reason through half-life right here. Half-life of this particular TM90 is 25 years. This means that half-life of any given quantity of this thing will disintegrate within 25 years. Okay, so this part A says, if a sample has a mass of 24 milligrams, find an expression for m of t, mass as a function of time. All right, now this is kind of interesting. Back when we were in Algebra 2, we gave you an exponential function that included e, which is what's on the next slide. What if we didn't want to use e? What if we wanted to figure out an exponential equation that didn't use e? Well, let's see. So mass at time 0. What is my mass at time 0? Well, starting mass is 24 milligrams. Okay, mass at time 25. Well, mass at time 25, what's going to be remaining after 25 years? How many milligrams? 12, right? I take 24, I bring it down to 12. How did we get that? Well, that's 1/2 of 24, right? Okay, well, what about mass at time 50? How much is going to be left over? 24 down to 12 down to 6, which is essentially 1/2 of 1/2 of 24, right? And I could keep this process going. I could say, well, what's the mass at 75? Well, that's 3, which is technically 1/2 of 1/2 of 1/2 of 24. And I could keep going and going and going and going. But is there any way we could create an equation from this? Well, this would be 1/2 to the first power times 24. This is 1/2 to the second power times 24. This is 1/2 to the third power times 24. So I could keep that going. 2 to the fourth power times 24, right? If I wanted m of 100. So how do I relate my input of time to this power? Well, what I'm really doing is saying, okay, if my input is time, this is the amount of half-life cycles that it's going through. It went through 0 cycles, 1 cycle, 2 cycles, 3 cycles, and 4 cycles of half-life, right? So what we can really say is 1/2 to the, because it's half-life, 1/2, 1/2 to the, and we're going to say t divided by 25 times the original amount of 24. That's my equation that's going to represent this function. 1/t divided by 1/2 to the t divided by 25. 25 was our half-life, right? If I take 100 divided by 25, I get 4, 1/2 to the fourth power. It's just interesting. The book does this, 2 to the negative t over 25 times 24. Okay. So this is our equation that models, and we didn't even use E. This is our equation that models the exponential decay of that function. Now, find the mass remaining after 40 years. Well, quite simply, if I want 40, we know it's somewhere in here, right? We know it's somewhere between 12 and 6, but we're not exactly sure what it is. Well, if I've created an equation for it, I can just plug it in. T to the negative, that's a pi. 2 to the, sorry, give me a second. Negative, and my time value is 40 divided by 25 times my initial amount, 24. So 7.92, we'll round it. 7.92 grams. Was it milligrams? Milligrams of this thing. To the nearest milligram? Okay, 8 milligrams. There you go. Use the graphing device to graph M of t and use the graph to estimate the time required for the mass to be reduced down to 5 milligrams. All right, so if I've got my equation now, it's pretty easy to plug in. Let me get this out of here. I want 2 to the negative x over 25, and then times 24. And I want to know if the y value needs, if the output needs to be 5, that's a y value of 5, where the x value is going to be the same. That's what I'm going to look for here. So I'm going to zoom 6 and let it run, get my graph to my standard 10 by 10 window. And then I am going, yeah, that's just horizontal. There's y equals 5 there. But what I'm going to do is I'm going to do zoom fit. That's going to be my best option. Because here's my exponential decay function coming down. There's my 5 coming across the bottom. So I want to figure out when these are going to intersect. So I'm going to zoom out. I know it's happening somewhere over there. So I'm going to zoom out. Zoom 3, enter. It's across. Oh, so close. One more time. Zoom 3. Oops. 3, enter. So here's my exponential coming down. We're not even going to see my second line, but we know it's going to cross now. So second, calculate the value, or sorry, the intersection. Choice 5, first curve, enter, second curve, enter, guess, enter. So when is it going to happen that it's going to get down to 5? It's going to be 56 point, just say to the nearest something. No, just to estimate, 56.6 years. 56.6 years. Which makes sense because if I wanted to get down to 5 milligrams, it's less than, it's less than 75 years. 75 years, it would have gotten all the way down to 3. And it's a little bit more than 50 years because 50 years gets it down to 6. So it makes sense that it's 56.6 years. 56.6 years. We got 6 minutes left. I'll do these 3 slides on Monday, but honestly, it should only take me like 5 minutes to do that. 5 to 10 minutes. Okay. So I'll stop there. If I wouldn't have had so many interruptions, could have gotten done. I'll be all right.